All right, we're going to begin the morning session with reading Spacetime Inversions.
All right. So thanks for the invitation. It's great to be back. Nice to see all these people who I love again. So yeah, I'm going to talk about work with Tokiro Numasawa, who is somewhere. Numasawa-san, are you? Oh, here you are. Okay. Yes. On gauging space-time inversions. So I'll begin with at least an apparent tension between two statements that I think are true about quantum gravity. So the first is that CRT is a symmetry in quantum gravity. Now, just as a notational aside, people often talk about CPT symmetry. That makes sense in even space-time dimensions. The thing that always makes sense is a rotation by pi in Euclidean signature, which gives you a reflection in one spatial direction. So R here means a reflection in one spatial direction. Okay. So this, of course, is something that, because we don't know what quantum gravity is in general, so I can't prove this statement to you. I can give evidence. For example, it's certainly true in ADS-CFT, because in ADS-CFT, it's dual to a conventional quantum field theory on the boundary. And in quantum field theory, there's certainly the CRT theorem. Okay. It's also true in string perturbation theory, because if you are working in a vacuum that has Minkowski signature in some number of dimensions, then you can do a rotation by pi and Euclidean signature in the target space. So the string scattering amplitude will be CRT invariant. On the other hand, there's also a conjecture, proposal, assumption for this talk, which is that in quantum gravity, there are no global symmetries. So this idea goes back a long way. There was a nice review by Banks and Seiberg about 13 years ago, presenting sort of the heuristic black hole argument, at least when the symmetry is continuous. In the context of ADS-CFT, Hiroshi and I had a holographic argument. And then with Edgar, who's also somewhere, I don't know, or maybe it's too early in the morning for Edgar. Oh, all right. We had an argument that at least if this island picture of the unitarity of black hole evaporation is correct, then that's also not compatible with global symmetries. The only way out of this tension is that CRT should be a gauge symmetry. Okay. And more generally, any space-time inversion symmetry which is not broken. So in our universe, T and R separately are not symmetries, or CT or any of them, but in other vacua they could be. And whenever they're symmetries, then they have to be gauged. Now, in Euclidean signature, there's a long history of doing this, especially going back to the world sheet of the unoriented string, where people say that you start with the oriented string and you gauge world sheet parity, and that gives you the unoriented string world sheet. So in Euclidean signature, that's kind of the end of the story, at least for gauging R or CT. It's just do you include unoriented manifolds in addition to oriented ones. In Lorentzian signature, though, things are a little more confusing. And so in this talk, that's really what we're going to be trying to do, is to understand this in Lorentzian signature. So just to give you an example of the kind of trouble that you can get into. So here is an example of what you might call a non-trivial gauge configuration for time reversal T, right? So I call this the Lorentzian Mobius strip. So you have a spatial circle, and you go around the spatial circle. And when you come back, time is going in the opposite direction. Okay, so that's like, if you like, this is a space-time with holonomy for time reversal. So, why doesn't this lead to causal pathologies, right? Or maybe it does, right? But then what do we make of that? And indeed, you could ask, is it even possible to do quantum field theory in a space-time like this? And actually, there are arguments in the literature from the kind of more algebraic point of view, arguing that it doesn't make sense. Okay, and if you really think that it doesn't make sense, well, now this issue of the previous slide is really a problem, because I've argued that you need to include things like this, and so they had better make sense. And my goal today is to make sense of them. So yeah, this is what we're going to focus on: saying what it means to gauge space-time inversions in Lorentzian signature, and since the talk is short, I'll just focus on time reversal. So in the paper, we also talk about gauging R. So here's the plan. So we'll first review what it means to gauge discrete internal symmetries. So this is something where for certain people it's well known, for other people they never thought about it before and think it's confusing. So I'll try to bring everyone up to speed. Then I'll talk about background gauge fields for space-time inversions in quantum field theory. So for example, like the background we just looked at. I'll then give an example from ADS CFT where you need to include a geometry which is not time-orientable to match a boundary calculation, okay? Which to me is fairly convincing argument that we got to tolerate these things. And then finally, I'll make some comments about what this means for quantum mechanics in a closed universe. There's a sort of fun story there. And yeah, so this is based on this paper with Numasawa-san. Okay, so let's start with reviewing the internal case. So I'll start formally and then try to make it a little more practical. So in general, for any group G, the definition of a background gauge field is that it's a connection on a principal G bundle over M, where M is space-time. Okay, that's what you learn in kindergarten or whatever. So when G is discrete, life is simpler. So then what you need is a rule that assigns a G holonomy to each loop in M that tells you for any loop in the space-time, if you go around the loop, what is the gauge transformation that you come back by. So more formally, a background gauge field is a homomorphism W from the fundamental group of the manifold to G. And then that's not quite right. You have to do an equivalence relation because at the base point of the loop, you could do a gauge transformation that conjugates the holonomy. So to get something gauge invariant, you should identify holonomies that differ by conjugation by an element of G. Okay. Now, in practice, if you want to turn on a background gauge field for an internal discrete symmetry, you do this by taking the symmetry operator U of G, right, the operator that implements the global symmetry on the Hilbert space, and then wrapping it on the cycles that are dual to the one cycles where you want the holonomy to be. So here's a simple example, right? If I want to have a holonomy going around this circle, I take U of G and I extend it this way. And then you see if I take a charged operator and I try to move it around the circle, it kind of gets stuck on the symmetry operator, and you have to pull off a piece of the symmetry operator and drag it around with you. And that just, when you wrap the operator by the symmetry operator, that just implements the symmetry and gives you D of G times O, okay? And so in practice, that's how you turn on a background gauge field for discrete internal symmetry. So I want to emphasize for future reference that in the case where it's a global symmetry and you're just viewing it as a background field in this construction, you can actually detect the location of this U of G using the charged operators. There is a codimension 1 surface where when you move operators across it, they suddenly transform. So it's only once you gauge the symmetry, right, where you sum over the backgrounds, this we're going to do in a minute, that you lose this ability to detect the location, and then you're really just depending on the homomorphism and not on this additional data of where the surface is. Okay, so now let's gauge the symmetry. So then, of course, what we're supposed to do is we're supposed to sum over background gauge fields and then divide by the size of the group. And in principle, you can add terms to the Lagrangian when you do this, right? So like in the continuous case, you can add a kinetic term for the gauge field if you wish, in addition to summing the theory without the kinetic term. And that's true in the discrete case also. There are sort of, quote, kinetic terms that you can add. So let's just do an example. So let's say that we're working on a torus, and let's say that we're gauging a Z2 symmetry. So then in this sum, there are 4 terms, right? There's a term, so these dotted lines here are the symmetry operators, U of G. The 1 plus 1 is confusing because codimension 1 is also 1, but so the dotted lines here, I mean the symmetry operators. So, so here there's no holonomy. In this case, there's a holonomy in the time direction because the symmetry operator is wrapped on the spatial circle. Here there's a holonomy in the space direction, and here there's a holonomy in both directions. And the Hilbert space interpretation of this is that the first 2 terms here are a projection onto the singlet sector of the ungauged theory, okay? And then the second two terms are projecting onto singlets in a new sector, which I guess in string theory we call the twisted sector, the sector where as you go around in space, there's a holonomy for the field. So this is a different, these two live in a different Hilbert space than these two, and they're the twisted sector. Now, I'm not going to say more about this in this talk, but I should just emphasize that in this term, we have to deal with the intersection of these two operators, which in principle can cause some difficulty with how do you resolve that, right? It's a UV sensitive thing when you have two operators that are intersecting. So if you can't consistently define this intersection, then you say that the symmetry has an anomaly. So there's a nice paper by Lin and Xiao emphasizing that in this case, although of course the idea goes back further. So in this talk, I'm not going to worry about anomalies. Anything I gauge is not going to be anomalous. So examples of this construction, right? So they're familiar in 2D, right? If you have a compact scalar, you can do the orbifold of phi goes to minus phi. And then this language is very familiar. Another example is if you think about the critical Ising model, there's fermion parity, and you can think of these four terms as imposing the sum over spin structure. So in the Ising model, people often say it's dual to a free Majorana fermion, but this is not correct. It's a free Majorana fermion with fermion parity gauged, or summed over spin structures, if you like. I guess in string theory, it's also called the GSO projection. Okay, so that's the end of the review for the internal case. Let's go on. So I'll skip doing R because I don't have much time. I'll just go straight to time reversal. So doing the holonomy in the time direction is not so mysterious. Well, we'll talk about it later. That's projecting onto T invariant states. For now, let's think about trying to define the twisted sector. So the twisted sector, so if we do a free scalar and 1 + 1, say, then it says that if you go around, so here I'll take the spatial circumference to be L. So if I go around the spatial circle, when I come back, time has changed direction. Okay, so this should define the twisted Hilbert space. Now, classically, this is actually not so bad, right? So this theory has a kind of reasonable looking initial value formalism at t = 0, right? So what does this boundary condition say? It says that phi is periodic as we go around t = 0, but phi dot is anti-periodic. Okay, but that's a sort of reasonable set of initial data. Had I put a plus sign here, I would have just gotten the initial data of the field theory on a cylinder, so it doesn't look that different. And indeed, you can write down a complete set of solutions. The details don't matter, but this is what the solutions look like. So for any point in that set of initial data, you can write down a solution like this that realizes it. So classically, there's a fine set of solutions of the wave equation. Where you start to get a little bit into trouble is when you try to construct the symplectic form. So in quantum mechanical language, you try to impose canonical commutation relations. And there's a puzzle because there's a phi dot here. Okay, and so if you think about that on this, because time flips as they go around, this equation can't be smoothly imposed everywhere on this t = 0 surface. As we go around, there has to be a discontinuity somewhere. Okay, and so this is one of the two reasons why in this old literature, people argue that you can't do quantum field theory in this geometry. Okay. Now, our interpretation is going to be different, though. We're just going to say that this discontinuity is fine. We should just think of it as the location of the symmetry operator, right? And we saw even in the internal case, if you put a U of G here, then there is a discontinuity as you move operators around a circle. And we'll just accept that. You know, the only thing that we'll require is that once we gauge the symmetry, then this discontinuity goes away. And that's true here, right? Because if we gauge a symmetry, then phi dot is not T invariant. And so this equation doesn't need to be, there will be no discontinuity in terms of gauge invariant things. So in some sense, that's kind of it. That's the theory, right? You impose this just allowing for a discontinuity somewhere. That defines the Hilbert space. Another way to say it is the Hilbert space is wave functionals on which d phi flips sign at x = 0, and there's a special point. It's the point where this flips sign. In practice, though, you kind of run into an issue here because there's no time translation symmetry of this, right? The boundary condition breaks time translation symmetry. So there's not a ground state that you can compute correlators in. I mean, and there's not really any other particularly natural state either. And so although the theory has a fine Hilbert space and it represents the canonical commutation relation, so in some sense we're done, we can compute Heisenberg operators, but what do we compute, what states do we use, right? So I mean, of course, that, for example, in de Sitter, it's also true that there's no time translation symmetry. What we do there to get a natural state is we use the Euclidean path integral. And so we can try to do that here. So let's try to do that here. So we can take the Euclidean Mobius strip and try to use it to make a state. So, I could put some initial conditions, some final conditions here, and then I can identify this with this and this with that. So you see that won't be a pure state, right? Because the identification is mixing the bra and the ket, but we could hope that it's a mixed state at least. So we could try to define the matrix elements of some density matrix rho hat. But actually, even this doesn't work because we'll see in a minute that this is not a positive operator. Okay, so we'll call this Mobius pseudo state because it's not actually a state. I emphasize this is not like a radical modification of quantum mechanics. This is just the system doesn't have a natural state. So we have to figure out what we're going to compute. Okay. So in fact, in the past, this lack of a natural state, this was the second argument used in these papers to say that you can't do quantum field theory in a unoriented background, because they tried to make a 2-point function that had all the symmetries and it wasn't positive. But okay, too bad. So indeed, our attitude is just, well, we have to think a little harder about what to compute. The theory is fine. We just have to find some good computables. And indeed, the computables that we'll do is we'll just sort of embrace the pseudo state. So we'll say, okay, it's not really a state, but we can compute trace of rho hat times Heisenberg operators and see what we get. And although that won't necessarily have a simple physical interpretation to diagnose the theory, we can study the properties of these correlation functions just to get a handle on what's going on. So I'll spare you the details of the correlators. This is what they look like, but I'm not even going to give you long enough time. These are the Whiteman functions here, but I'm not going to give you enough time. Yeah, big derivatives because it's the 1 + 1 scalar. It has a log, blah, blah, blah. So, okay. I'll just tell you the lesson of the correlators, which is that if I take a spatial slice, say here's the t = 0 slice, just for fun, I took a different spatial slice here. And then you get the diamond, which is sitting on top of that slice, the discontinuous point. So here the discontinuous point is at the edge. So I take the dependence of this slice, but removing that point. So I get this gray diamond. Then the correlators are totally conventional in this region. They don't have any spurious singularities. And in particular, the Whiteman function is compatible with the canonical commutation relations being imposed on the surface here. Okay, so on the other hand, though, the algebra gets more complicated outside of this region. For example, essentially because this geometry has what I'll call self-intersecting time-like curves. So here's an example of one, right? I come in here on my time-like curve, I come out down there, and there's a self-intersection. So it's not quite a close time-like curve. So in a time-orientable geometry, a self-intersecting time-like curve can be deformed into a time-like curve. And so relativists usually use closed time-like curve as the criterion for causal pathology. But when things are not time-orientable, you should really use self-intersecting time-like curves, because since the self-intersection happens going in different directions in time, you can't deform it into a closed time-like curve. But I think it's still bad, right? You meet a future version of yourself going backward in time. I don't know. So we should use ITCs instead of CTCs as the sign of trouble. Okay, and so you might say, okay, so the lesson here is there's kind of a good region, the gray region, and then outside of that region, the theory still makes sense. I can solve the Heisenberg equations all the way up and down and compute correlators. But life would be pretty weird if you were down here. I don't think so. I think I can compute, yeah.
You have the self-intersection.
I think as long as I smear things, be okay. I mean, yeah, I think if I normal order and then smear, it should be okay.
think the operator product expansion would just catastrophically fail outside the.
I think there'll just be more singularities, right? So if you look at these correlation functions, right, there's like a sine and a cosine, right? So these functions have lots of singularities because of the sine and the cosine have many zeros. They're all resolved by the I epsilon prescription. Well, I don't know. I didn't think about it. I guess that. I'd have to compute it, so I don't want to try to guess the answer, but I feel like it should be fine. But yeah, okay, Ahmed.
Curve by going through the boundary one more time?
No, it's kind of funny, right? So say I come up here, I go down there, but now if I go through here, come back out up here going that way.
No, go through the other one.
No, either way, if I come out here, still I come out there going that way.
Oh, is it? Oh, I see.
Yeah, because when you come down this way, you come out that way. So I think this actually does not have closed time like curves.
It's not just reversing the time, but
yeah.
Okay.
Yeah. Okay. So in 2D CFT, I can give you a rather explicit characterization of the Mobius pseudostate, so that we can see in particular that it's not positive. So the state is defined like this. I can just take the top half and kind of flip it over and plop it down here next to the bottom half. Okay, that costs me a time reversal up here on the state that I'm projecting onto. But you see now the identification is a lot more civilized, right? You see here, this is just because these are going the same way, those are going the same way. And so this is really just the ground state wave function of the theory on a cylinder that's twice as big, okay? But you have this time reversal here on half of the system, okay? So if you chase this through, what this tells you is that the pseudostate is equal to e to the minus pi times the modular Hamiltonian of half the cylinder that's twice as big in the usual ground state. So this is positive, but then multiplied by CRT and also by time reversal, okay? And so the product of these two is a unitary operator. So the lesson here is that the pseudostate is a positive operator times a unitary operator, which of course is not something that has to be positive. Okay, so that's it for this example. Go on to ADS CFT. Oh yeah, Nati. No. So remember, this is a background for T. So I have to assume that there's T symmetry for this discussion, which there is for the free scalar. Yeah, you can, but if you're thinking of it as a background field, then I mean maybe it's a matter of definition. So I was defining the background field as the network of U of G operators. Yeah. No, that's true, but I guess there's a question of what space do the correlation functions live on? So there will be a monodromy of the correlation function, however you go around. So if you want the correlation to be a defined function, you have to pick a location, right? If I ask you, what's the correlation function right at this point? I mean, I think it's similar to saying I want to define the square root of z. So if I want to have a rule for you give me a z and I tell you what the square root is, I have to pick a location for the branch cut. I agree that once the symmetry is gauged, this is unphysical. But it's just because if I want to give you a function, I have to make this choice. I don't think it's deep. Yeah. Oh, I think for questions on the Zoom, let's answer at the end, okay? Yeah. Okay, so let's go on to do an example from ADS CFT. Okay, so now, okay, maybe you're thinking I'm crazy, although just wait, it's going to get even worse. But first, let me try to force this on you so that you can't escape using ADS CFT. Okay, so I'll try to give you an example where all the things I just said happen in ADS CFT. So let's first. So this is going to be an example from ADS 3 CFT2. So let me first remind you. So in Lorentzian signature, right, you can have the BTZ geometry. So this is the maximally extended BTZ. There's a circle that's sitting on top of this, which does not contract anywhere except at the singularities. I'm going to work in Kruskal coordinates where time goes like this and x goes like that. Okay. And then we can also do the Euclidean BTZ where it's a disk times a circle, a disk of circumference beta on the boundary. Well, on the left side, we usually work in the Harlow-Hawking state, right, and compute correlators, whatever. On the right, we view this as computing the CFT thermal partition function. There's some formula here that everybody knows that you can write either in terms of G Newton or in terms of the central charge of the CFT. Okay. All right, now we're going to mutilate this. So I'm going to make a new geometry, which I call the CRT twisted black hole. So in Lorentzian signature, I start with the BTZ in Kruskal coordinates, and then I do the following identification. So I identify any 2 points which differ by flipping the sign of both t and x, the Kruskal coordinates, right? So in the previous picture, it's like this point gets identified with that point. But then I also throw in a rotation by pi in the circle direction for the circle that's sitting on top of the picture, okay? So because of that rotation by pi, there are no fixed points of this identification. So this generates a smooth Lorentzian manifold, at least away from the singularities, that were already singular to begin with. On the right, I've kind of drawn the Penrose diagram. So since this sends x to minus x, I can take a fundamental region to just be kind of the right half of the Penrose diagram. But then it looks like there's something in the center here, but there really isn't. It's a smooth geometry. And so say if I come in up here, then I just come out down there on the other side of the circle and going backward in time. Okay. So it's a time non-orientable geometry. This is what the whole geometry looks like. You can view it as taking the space between these two cylinders. So the blue cylinder is the ADS boundary. And then the inner cylinder is, I do this sort of antipodal identification on the inner cylinder that, that does the antipodal circle and reverses time, okay? So in fact, this internal cylinder becomes the Lorentzian Mobius strip. So this identification on the cylinder, it gives you exactly this Lorentzian Mobius strip we talked about before. So I want to emphasize this is a smooth asymptotically ADS Lorentzian manifold. The boundary is like maximally kosher, okay? It's just the cylinder, right? It's the usual Lorentzian cylinder. You can't complain about the boundary here at all. It's only weird in the bulk, all right? And so if your rule for ADS CFT is you have to sum over asymptotically ADS Lorentzian manifolds that match this cylinder boundary, then this is a candidate that you have to consider, okay? And here, by the way, if you like, it's enough to just gauge CRT here. I don't even need time reversal to do this, right? And CRT is always a symmetry, so you can't escape including this. On the other hand, right, it's not time orientable and it has self-intersecting time-like curves, right? This locus here is just the Lorentzian Mobius strip, so we can have the same discussion that we had before. So as in the case of the Lorentzian Mobius strip, there's an issue of the choice of state. So there's not a natural state, meaning a positive density operator that you can choose for this geometry, but as in the Lorentzian case, there's a natural pseudo-state, which you get. So here's the bulk picture. You have a sort of initial state and a final state, but then you do this identification here and here on the sides to give you some state that you can prepare on this time slice. If you ask what that means on the boundary, well, it's like I have, so I'll write the equation. So you have an initial state here. You evolve by beta over 4. So remember, it's beta going all the way around. Okay, so from here to here is beta over 4. Okay, that's this. Then in this gluing, remember, it has that rotation by pi. So I have to put in an e to the I pi j here and then glue down there. So that's this matrix multiplication here. And then from down here, I evolve back up by another beta over 4, okay? So the pseudostate, so h and j commute. So I can write the pseudostate as the positive operator e to the minus beta h over 2 times the unitary e to the I pi j, just like what we saw for the Lorentzian Mobius strip, okay? So that's the natural state or pseudostate to consider here. We can actually check this proposal because it's ADS3. We can show that this is really there. in two different ways. So what we can first do is compute the trace of the pseudostate, right? So just the trace of this operator. Okay, so let's first compute it in the bulk. So in the bulk, what we should do is we should just evaluate the Euclidean action. We should sum over these things here. So it just gives us this half of the Euclidean cylinder with this funny identification here. We should just evaluate the Einstein action. Okay, but it's just half of the BTZ geometry. So I should just put a 1/2 in the exponent, or take the square root of the partition function either way. So I get this. All right. On the other hand, we can do the CFT calculation using cardiology. So this is just a torus partition function. But the complex structure parameter tau is 1/2 plus I beta over 4 pi. So let's call beta over 4 pi epsilon, because we want to be thinking in the high temperature regime. So beta will be small. Okay, so here we go. So we want to compute ZCFT of 1/2 plus I epsilon. So we send tau to -1 over tau. Then here I do a Taylor expansion. So this is like this. Then I do 2 T transformations to get rid of the -2. And then I invert again. Tau goes to -1 over tau. And now this is a standard low temperature CFT partition function, which I can compute using the Casimir energy. And I get this, which wonderful is that. Okay. And so we see that this CRT twisted black hole is indeed the dominant saddle point contributing to this CFT calculation. Okay, had we not included it, we would have gotten the wrong answer. Now, you could complain, you could say, well, that's too Euclidean. The whole point here was to be in Lorentzian signature. Okay, fair. So let's look at the 2-point function. So we can compute the Whiteman function, meaning the trace of phi of t, phi of 0 against this funny operator, right? So we can compute it in the bulk by using the method of images. And we can also try to compute it in the boundary. Now, if we were strong CFT people, we would compute it using the torus-Virasoro identity block. Okay, but that was too scary. So what we did instead was we just computed it in the Ising CFT. And at high temperature, it should be universal. So whatever you get in the Ising model should be the same as what you would have gotten from the Virasoro identity block on the torus. And indeed, you can see it works. So here, the solid line here is the holographic answer for the real part of the Whiteman function and the imaginary part, and the dashed line is the Ising CFT. Okay, and so again, this 2-point function, you'll just get the wrong answer if you don't include the Lorentzian 2-point function computed in this funny pseudostate. Okay, now you could say, well, what about boundary causality? So, okay, let me just see, I'm getting close here, okay. So the CRT twisted black hole has some weird causal features. So here I've drawn some causal curves. So if you go from the boundary to the boundary, that's okay, that looks reasonable. If you jump in, right, you can do funny things like go there and then come out here and end up in the past singularity, which anyways, the past singularity is connected to the future singularity up here. That's still not so bad, but then if you start in the past singularity, you can kind of do this, come back and have one of these self-intersections, okay? But I want to emphasize that you see that self-intersection is behind the horizon. So if you're just living out here, everything seems fine. And indeed, everything does seem to be consistent with boundary causality, because any curve that starts and ends on the boundary is not going to run into one of these self-intersections. Yeah, Ahmed. Yeah.
To make this black hole in some sense escapable.
Yeah. Yeah, I agree. But I think then the coupling would also violate boundary causality. And so then you could try to have a consistent story like that. Yeah.
Have a consistent story because it's not really a state, right? It's not.
But it's still true that the operators in the CFT should commute at space-like separation. So that's an algebraic statement. It should be true in the expectation value of this pseudostate. Yeah. So in fact, what I would say is that this region outside of the horizon is like that gray region we had before in the Lorentzian Mobius strip. So there's a region where things are good, and then there's a region where things are not good. And what I would propose is something we call chronological censorship, which is a relaxation of Hawking's chronology protection conjecture. So Hawking's conjecture said no closed time-like curves. Okay, now he didn't know about time unorientable things, so what he should have said was no self-intersecting time-like curves. but that's too strong. So with this, what we say instead is that self-intersections are okay, but they have to be behind horizons. Okay, so that's what we would call the chronological censorship. Okay. I think I'll skip this. This is the general story of what it means to gauge R and T. The idea is it's a statement about the structure group of the tangent bundle. Okay, so far I was doing examples, but if you want a rule for what it means in general, it has to do with how much you can reduce the structure group of the tangent bundle. Okay, all right. One more slide, okay? So let me just comment on quantum cosmology because this is kind of fun. So the gauging of any symmetry involving T is particularly subtle in the context of a closed universe. So say if we were living in S3. And the reason is that in a closed universe, all physical states have to be gauge invariant. So in electromagnetism, right, that's a consequence of Gauss's law. That's also true for discrete symmetries, by the way. In the case of anti-unitary symmetries, though, you get something quite surprising. So if psi and phi are linearly independent CRT invariant states, then if I form a superposition, the superposition is only CRT invariant if the coefficients are real in the superposition. So in other words, what you learn is that the Hilbert space of quantum gravity in a closed universe is a real vector space. Now, this, I think, is correct. It's kind of a surprising statement. If we think, which I'm not totally sure, but if we think that there is a holographic dual of cosmology in a closed universe, then this should be a baked-in feature. It should be true that the Hilbert space of the dual theory of cosmology in a closed universe has a real vector space. And okay, I don't know what kind of theory would naturally do that, but it's fun to think about. Now you may complain, you could say, come on, Daniel, I mean, in quantum mechanics, right, like all the good stuff depends on the phases, right? You learn about the double slit experiment, Shor's algorithm, whatever. Why aren't I just mutilating quantum mechanics by saying the Hilbert space is real? So this is the last thing I'm going to say. So the reason it doesn't ruin quantum mechanics goes back to this old thing in cosmology that you need to have a clock, okay, to make sense of observations in a closed universe. So indeed, say that we have some state psi of some system, something in the universe, and then we take a clock. So to do time reversal, usually a clock needs to tell you what time it is. I only need a clock that tells me whether time is going forward or backwards. So it's a two-state clock, right? And it's this C here. So given any state of some object in the system, I can make a CRT invariant state by superposing the clock going forward with that state plus the clock going backwards with the CRT conjugate of that state. So this is a CRT invariant state. It lives in this real Hilbert space, whatever state I choose for psi, right? Similarly, when I define observables, I can say, okay, I want to see if the system is in the state chi, but then I also check if the clock is going forward. And if instead the clock is going backward, then I see if the system is in the CRT conjugate state, okay? And this again is a CRT invariant operator. Technically here I'm assuming CRT squares to 1. If they're fermions, it's more complicated, but it also works. You need to sum over more. Your clock needs 4 states, okay? And then you can just check simple algebra that if I compute the expectation value of this projector in this state, I get exactly what I would have gotten from following the ordinary rules of quantum mechanics on the system S using complex states. For any states in the system. Now, you might say this just seems like bookkeeping, right? I just, come on, Daniel. Okay, fine. You can take any quantum system, you can add 1 degree of freedom and make the Hilbert space real. Okay, but I don't think it's just bookkeeping. And the reason is that the clock needs to be part of the system. So this calculation is only correct in the limit of an infinitely big universe. When the universe is finite, the clock is something there. It's a finite distance from the system. And this CRT that acts just on the system doesn't really make sense. Only the CRT on the whole system makes sense. So if you like, what I'm saying is that when the universe is finite, there are corrections to quantum mechanics coming from the fact that the real Hilbert space is real. Okay. All right, so let me end. So we've learned some fun things. So gauging space-time. Actually, I didn't actually show this. I skipped that, so I apologize. It's an earlier version of the talk. So we showed that quantum field theory makes sense on backgrounds which are not time-orientable but doesn't have a preferred state. In ADS-CFT, it's necessary to include these time-orientable unorientable geometries. In a closed universe, the Hilbert space of quantum gravity is real. I didn't have time to explain, but actually I wrote it here twice. So open strings are twisted states from gauging world sheet parity. That's a fun story. So if you like string theory, ask me about it. And also in quantum cosmology, the gauging of CRT prefers the Harlow-Hawking state to the Vilenkin tunneling state. So if you know about that, that's what it says. All right, thanks for listening. Sorry for going all over.
So in ADS-CFT, I'm used to thinking that the Hilbert space on the boundary agrees with the Hilbert space in the bulk.
Yeah,
And now you've introduced these pseudo-states.
yeah.
So that seems like a generalization of what we were calling bulk states.
Well, no, sorry. So I remember the bulk has a conventional Hilbert space.
Even in this case, there are normal states there. It's just that there aren't any particularly nice ones to talk about. So roughly speaking, what I would say is the Hilbert space here in the CFT is the same as before, right? It's the Lorentzian cylinder, so it's just the Hilbert space of the CFT. So what I would say is some of those states, it's kind of hard for me to tell you which ones, but some of them correspond to bulk states which are in this Hilbert space instead of bulk states which are in the you know, like say the ADS vacuum with some dust in it or something.
State, can it be written as some maybe complicated
Yes.
superposition of the usual state?
Yeah, that's right, exactly. So it's
Some operator on the Hilbert space of usual states. It's just that if you ask me which CFT states correspond to this, it's hard for me to tell you, you know, because there's no particularly natural one for me to pick. So I use the pseudo state as a way at getting at that part of the Hilbert space without being able to tell you, you know, which ones are which pure states are like this.
To call the pseudo-state linear combination of states, or
well, it's an operator. No,
It's an operator on the Hilbert space of states. That's what it is. Yeah. So yeah, that's why I use the word computable, right? I don't. This correlator is not observable. It's a computable. Yeah. Oh yeah. If does the Zoom? On the Zoom, if you can raise your hand again if you have a question, maybe.
There was one question. I'll let you get the question that was.
Okay. Well, let's give them a chance. So yeah. Yeah.
I thought discuss some black holes,
yeah,
which I think are, well, in the 3D case, it's the same as your question.
yes.
So I think you've given an interpretation of what those spacetimes are. So they're pseudo-states.
Yeah, I think that's correct. Yeah, yeah. So Tuft talked about the four-dimensional version of this. So in the four-dimensional case, this identification is orientation inversing. So you need to have parity symmetry because antipodal map on a two-sphere is a orientation inversing.
So Tuft's thing only works in theories with parity symmetry, but then when you have it, then yes, I think this should be the similar story. There should be a pseudo state. Yeah, I never understood what a Tuft is saying about these things, but okay. Yeah.
Let's just get the Zoom and then Ellie will get to you in a second. Okay, so the question, can you unmute yourself?
There's something in the chat. I don't. Yeah, we see you. Can you talk, Angaran?
Yeah. Hi, Daniel. Yeah, thanks for the nice talk. Yeah. So on the point regarding quantum cosmology, so you talk about the fact that the anti-unitary operation of well, I guess this is what you're saying was a CRT or just T reversal by itself is anti-unitary, but that involved states being the coefficients being complex conjugated because of the anti-unitary operation. But don't you also have to flip T to minus T in those ket states that you had on that slide? So are you not inherently assuming that those states are invariant under T going to minus T?
Yeah, so I think it only makes sense to gauge time reversal in situations where time translation is also gauged. It doesn't make much sense to gauge space-time inversions purely in quantum field theory. I think you also want to be in quantum gravity, and so then the choice of T equals 0 doesn't matter very much.
Right. Okay. Yeah. Thank you.
Actually, just to comment on what Juan said, there was another paper by Olga and Panos, I think maybe they are here, where they were talking about this Tuft thing in the context of gauging CRT. Yeah.
Professor Colin,
as you said, there's a well-known example with such gauging, which is the string on a non-orientable manifold.
Yes.
So are any of the peculiarities, so let's view it as a two-dimensional gravity.
Yes.
Can you demonstrate the peculiarities you pointed out in that system that everybody understands?
Yes. Yeah, I mean, I was essentially doing that with the Lorentzian Mobius strip. in the case where you gauge parity, there's, yeah, I didn't have time to explain it, but there's this interesting question of what are the twisted states of gauging parity. And in the literature, there were claims by Signati and Harlow that the open strings should be the twisted states of gauging world-sheet parity.
Yeah, but in the
And
bosonic.
that follows from our rules.
Yeah, but in the bosonic string, you can study just the non-orientable string without.
In perturbation theory, you can.
But I think it's non-perturbatively inconsistent. I had a discussion with Emil Martinic about this. So if you try to formulate it non-perturbatively using a matrix model, then you end up having the open strings.
SP or SO matrix model, and then you sum over unoriented world sheets.
That's also true in the bosonic string.
So I agree it's different than the case
Of the orbifold, where there's a violation of unitarity and perturbation theory if you don't include the twisted states, or a violation of modularity. So that doesn't happen. But I think it's a more subtle problem if you don't include them. But I think you still need to include them. And certainly, for example, when you go from the 2B to type 1, by gauging worldsheet parity, you have to include.
No, I don't think it's because they're fermions.
Are you saying that the bosonic string on non-orientable manifold is more sick than the bosonic string on orientable?
Yes, if it doesn't have open strings. Yes.
What about the peculiarities with real Hilbert space?
So that's interesting. Yeah, so it's a little bit subtle. So there's a question of the CRT. So in the conventional discussion of the closed string Hilbert space, you don't gauge CRT, you treat it as a total symmetry. So the Hilbert space is complex. Then when you
Try to compute the string S matrix, I think implicitly now CRT is gauged because when you sum over Euclidean topologies, you essentially must be gauging CRT. But then try to give a Hilbert space interpretation of the string S matrix calculation in the worldsheet Hilbert space is confusing. It's not usually how we interpret that calculation. I think if we did, we would probably interpret it in a real Hilbert space. But usually we think of it as in the target space Hilbert space, which is like a different thing.
All right, let's thank Daniel again.